And we're back. Welcome back from Thanksgiving weekend and happy Tuesday. Today, we'll be going over a high level whirlwind introduction to deep learning. But before we begin, some administrative bits. The reading is this Nature paper on deep learning by Jeff Hinton. The last day of classes is the 3rd of December. Reading day is the 4th of December. Final exam period is 4:30 p.m. to 6:30 p.m. Tuesday, the 8th of December. That will be when you'll be doing project presentations. And the last day of finals, which will be Friday, the 11th of December at 8 p.m., which is when your final project will be due. So presentations on Tuesday, the 8th, and the code and the report on Friday, the 11th. I will post the final project on Thursday, this coming Thursday. Let's just get right into it. Machine learning versus deep learning. And the conversation for today is a high-level overview of deep learning. Now, it's funny that people say machine learning versus deep learning. And the content for today, I kind of culled from like 5 different sources, added a little bit of my own stuff. And when people say machine learning versus deep learning is a form of machine learning, right? It's a neural network. It's a class of functions whose parameters you are finding given a data set for the best description. All right, it's quite good if you have a lot of data, but the jury's still out about what happens if you have less data. And so you'll find a lot of arguments like machine learning versus deep learning, but deep learning is machine learning. It's a specialized subset of deep learning. But nonetheless, to go with a lot of the chatter that's out there on the subject, they talk about most machine learning methods working well is because of the human involvement. And so from your own experience with this class and the previous class before this in machine learning, you know that this idea of feature selection and feature design can play a dramatic role in the geometry of your data points. And we've talked about manifold methods that can do interesting things with that geometry to give you better distance measures so that you can draw better distinctions between the inputs from your in-sample points. And the hope is that if you have done it well enough, you can get out of sample performance that is quite good, i.e. generalization. Now, certainly the human aspect in terms of the domain knowledge, in terms of the design of features, is one big part of machine learning. And the goal is to select features that are really useful for discriminating or drawing distinctions between inputs of various types. Okay. That being said, you have this optimization problem, and that's to find the final best hypothesis, i.e. that hypothesis that best mimics the performance of the hidden target function on the in-sample data points. And so typically in practice, when you do machine learning, you have to understand a lot about your data, and usually you spend about as much as 65, maybe even more, percent of your time and effort and energy in dealing with features, right? And so oftentimes, some people say, well, it requires really specialized, graduate level training in order to get really, really good at this, right? And more, there's a recognition because every enterprise now traffics in a lot more data, regardless of if you're a computer science related enterprise. A lot more people are dealing with data and therefore are making use of machine learning methods and AI methods in general to make sense of whatever pattern information might be lurking within this data. And so the idea then is that you have your algorithm, like we talked about before, whose job it is to search through hypothesis space using the parameters of your model to try to find the hypothesis that best describes the target function on the in-sample points, its performance on the in-sample points. And so you describe your data with features using features that the computer can understand. And of course, for something like natural language processing or things dealing with text, that's just sort of a smattering, this table here, of various types of features you might use. You could use term frequency, histogram of the occurrences of the root stem words after you go through the stemming procedure to find the root words. You can look at its relationship to current words or previous words with these n-grams, bigrams, trigrams, or whatever. You can look at parts of speech. You can look at n-grams. You can look at words that go to your left, the words that come after you to the right. All sorts of different ways of describing features, and the goal is to choose a feature that is representative of the phenomena that you're trying to tease apart with respect to particular datums of interest. And so deep learning is different from machine learning here with this feature stage. You have your input, this top figure here or schematic. Um, you have your input, and there's this whole feature extraction component. And while feature extraction and feature selection is automated in, sort of, if you kind of think about it, is automated, but there's a lot of decision that the human in the loop makes, right? And so, of course, in even things like feature selection, you think about the process that gave you the data, and there's this dichotomy of linear versus nonlinear, and you use a nonlinear method if you believe that the data is nonlinear, right? So there's absolutely a human component involved, and then you train your classifier, and then you run your new data through it, you're out of sample points, and you get some performance. Now, of course, in deep learning, imagine now, instead of this human in the loop, you're taking your raw signal as it occurs from your sensing apparatus, and you're doing this feature extraction and classification. So this role played by the person, the crafting of these features, is performed by the system as it trains the classifier. And so that is the difference. And a deep learning algorithm tries to do this using multiple levels of representation. And the idea is to start with very simple representations, assemble them into increasingly complex representational components, and then use that against the classification performance, adjusting along the way. Any questions about this? And that's it. No, I'm joking. So there's more than this. So we talked about the following system at the outset of the semester when we talked about the architecture of a pattern recognition system. And in the middle here, between sensor and system evaluation, we had feature generation, feature selection, and classifier design, where for feature generation and selection, it's the process for creating your features and selection. It could be subset selection, or it could be feature synthesis, it could be linear, it could be nonlinear. And then we also have the classifier design, which represents the algorithm that searches through the space of hypotheses, looking for the final best hypothesis. So imagine now if you take these three stages in the middle, feature generation, feature selection, and classifier design. And that is essentially, if you notice here, we have these edges of feedback, right? And so the feature selection can inform choices of feature generation and vice versa. And the feature selection and feature generation can also influence the classifier design. And so if we take these three components along with the influences as noted here by the edge direction in this diagram, that's essentially what a deep learning network does. It combines all three. So not only are you learning what the final best hypothesis is, i.e. your classifier design, you're also learning the right way of creating features and the right way of selecting features that best impacts the ultimate performance as measured by your system evaluation. Does that make sense? And so a deep learning network is nothing more than a machine learning that, the classifier rather, and I shouldn't just say classifier, it could be regression, it could be all sorts of things, sequence learning, but it does this learning of features as well as the selection of features as it is learning the classifier. Okay, nothing more, nothing less, and it does that using a certain stylized type of functions as described by that graph giving you your network architecture. Okay, so people often, and this is when neural networks were still, were very, very new. Now, they're not new in compute terms because neural networks have been around early from the 50s and then the 70s and the 80s. And there was a lot of hype around it, and there was this thing called the AI winter that happened. People kind of overhyped what the technology could do, and it fell short. And there was a time when nobody would touch neural networks in terms of their PhD research and research in academia and in industry. But now with deep learning, there have been a lot of successes. And so now it is finally re-enjoying its time in the sunshine, so to speak. But if you go to neuroscience, one of the things that neural networks were trying to do, it was an effort to kind of understand what human intelligence and human cognition was. And if you look at the study, the format of a neuron in a neural network is just a very, very high-level representation, a very basic representation of the internet interconnects that happen between individual neurons in the brain. And so the interesting part about what happens in the brain is this idea of the one learning algorithm theory. It doesn't matter what sensory apparatus is inputting raw data into it. So if you have the auditory cortex and the visual cortex, here you have two different sensations. One is visual, one is auditory. So the raw data is very different from what you see versus what you hear, but nonetheless, they all go into the brain, and it's the same exact algorithm for neuroplasticity is what gives rise to your ability to learn and draw distinctions between patterns and extract features and do categorization. So the exciting part, in addition, about deep networks is here you have this raw input signal. And if we take a look back at this depiction of it as far as the architecture of a learning system is concerned, here you have a raw sensor. That raw sensor could be video frames, image frames from video. It could be audio information from a speaker. It could be all sorts of raw data coming into it. And it's the same exact algorithm in this deep learning network can now learn classifiers that can operate on these diverse sensory streams. And so that kind of matches a little bit this idea of the one learning algorithm, which is another particularly exciting aspect of deep learning, that you have the same back propagation and the same other learning methods, and it doesn't matter what the signal is inputted. You input the raw signal, and it decides what features are important, and it decides what complexes that are assembled from a set of features to make high-level features to describe things in the environment. Okay? All right. Any questions? Make sense? So it's just pretty exciting. And so, why is it useful? And so, a lot of times, anytime you have information, and the information that you get in its purest form from an artificial system comes from your sensors. And so, any choice you make, even the choices when you design features, you're throwing away information. Right? So when you say, I'm going to extract edges from an image, you're throwing away information that is not edge information. You're throwing away color. If you say, I'm going to represent color, I'm throwing away edge information. If you say, I'm going to take a histogram of color, you're throwing away the spatial relationships between colored elements in the image. And so every choice that you make for designing features, you're losing information, because a feature, after all, is just a summary of the raw signal information. And so when you have features that are learned from the data instead of designed, you can do two things. You can adapt them if something about the data changes. In addition, if you have enough data, you can learn them relatively effectively, and you know for sure that it'll be something that is useful for that particular type of data. So learned features are easy to adapt, and they're also fast to learn. And deep learning network provides flexible framework for how you represent things in the world. So if you have audio alone, it'll learn audio features. If you have visual features alone, it'll learn video features. If you have audio with video, it'll learn this unique combination of audio visual features, which is kind of cool, right? And all of this happens under the covers for you. You don't have to think about, how does my audio correlate with my video? And you don't have to pre-commit to these certain choices, like correlation with as a linear dependence. What if it's a nonlinear dependence? And throw away information that otherwise might have been very useful. And so the other part that's pretty interesting about the deep learning is that you can learn both unsupervised and supervised learning. So again, in supervised learning, you have categories like cat, dog, and so forth. And if you think about what a cat and a dog is, they both have four legs, so it's assembly of parts. They both have a head, eyes, and nose. But those head, eyes, and nose and parts, they're different sizes, they're different colors, they're different shapes, and the collection of them together gives you these categories. So there's this idea of semantic meaning. Moreover, in the unsupervised sense, you can group them together and say, this is Labradoodle-like, or this is Great Dane-like. And you can also now compute distributions over these natural associations based on the descriptions and do interesting things with these distributions, like sampling from them. So now you can produce something that looks dog-like and maybe tinker with that produced version of a dog and say, that kind of looks like a Great Dane, but it looks a little bit like, for example, a poodle and a lab, and then Labradoodle was born, right? Somebody crossed the two dogs. It looks like a poodle, looks like a lab. Guess what? right? So in the case of a deep learning network in an unsupervised sense, let's say you have images of poodles and images of labs. You have these two clusters. You compute distributions over them, and then when you get this new strange-looking thing, you'll notice, well, it looks like it belongs to this distribution of poodles and that distribution of labs. Let's put them together and call it a labradoodle, and they have degrees of membership in both of those. So you can do this interesting stuff um, without changing what you're doing. You have the raw signal that comes in, and then you have that one learning algorithm that works for you, kind of adjusting itself on the fly as you feed it more data. And so the interesting part is that you also can have effective end-to-end joint system learning. If you input multiple types of data sources, it will tease apart those associations for you instead of you having to commit to what it means to be linked together if you have cross-sensory types of signals coming in, so from more than one sensory mode. Um, it also needs large amounts of training data. That can be a benefit, and certainly that's possible now more recently rather than 20 years ago, even as close by as 20 years ago, because as society gets more and more digital, we have a lot more sensor data available. And so before, the idea of having data sets with millions of examples was unheard of. If you take, for example, as I was reading Tesla, the Tesla car, when you're just driving the Tesla car, right? It's not in autonomous mode. You're just driving it like a regular car. It's inputting data from its sensors and sending it wirelessly back to Tesla's data centers. So even if you're not driving in autonomous mode, it looks at what you're doing for steering, for braking, for accelerating, for turning, and all that good stuff. It looks at all of those control signals you're giving it, in addition to all the signals for LiDAR, radar, and video. And it's saying, this is what normal driving looks like. So it's always collecting this data, even if it's not in autonomous mode. And so you can imagine across all the instances of the Tesla vehicles that are out there, right? There are many of them. And across all the time that's spent driving, not in autonomous mode, that's a lot of data, right? Just for that one application. And so the abundance of data has made this possible. And so the jury is also out about what happens in the limit if the number of examples goes to zero, approaches zero, what happens to your algorithm? Um, in 2010, about 9 years ago, deep learning models started to outperform other machine learning techniques that included the human in the loop for the feature engineering part of it, right? And that's where it started to really catch people's attention, right? And this was in computer vision applications. And the nice thing about computer vision, right, you see your results. So that was pretty exciting. And in speech production, NLP, and auto completion, right? And so a lot of excitement happened in 2010, and deep learning started to really take off. And in fact, as a friend of mine in Silicon Valley, or formerly in Silicon Valley, now in Austin, Texas, tells me that there are people who are getting trained in deep learning, starting consultancy, and pulling in $500,000 a year. Will the gravy dry up at some point? Probably, but right now, there's a lot of delicious low-hanging fruit, as I've been told, as it pertains to deep learning. And that's only going to grow in the next 10 years. How far it goes, I'm not sure, but certainly more and more industries are now discovering data. And in fact, for modern enterprises, people are asking them, what is your AI strategy? Because data is really important regardless of what your domain is. And so, anyway, so it's exciting. It does a lot of stuff. It's very useful. And this graph comes from Andrew Ng. It's well, I guess it was Stanford, and then uh, Coursera, and then Baidu, and I can't remember what he's doing now. But this talks about the relative performance of, and it's funny for me to read this, traditional ML algorithms. I'll call it human in the pipeline, human in the processing pipeline, human IP, HIP, HIP ML, right? HIP ML versus deep learning. In HIP ML, that's where the human, the engineer, the scientist has input on what the features are, right? And therefore what the classifier and the learning algorithm is. And in deep learning, of course, it does that for you from the raw sensor stream. And so as the amount of data has increased, traditional machine learning algorithms have sort of started to peter out in terms of the increasing in performance. And deep learning algorithms are continuing to increase. And that point where they intersect, the red and the blue curve, is right around 2010, when deep learning has done really well. And so if you think of all the Siri agents, all the Amazon Alexas, that's a lot of voice data aggregated across the millions of people that use it. And if you think about what happens worldwide, you have all sorts of millions, many hundreds of millions of people that are inputting data. So it's pretty interesting. So deep learning is here to stay. So let's talk about some of these wins that are particularly interesting. So generative models. And in a generative model, essentially you're trying to find the probability that best generates some data. Now, if you can find the probability that generates the data, one of the things that this generative model affords you the ability to do is sample. And so now if that model represents images in a video, by sampling from it, you can produce artificial videos that look really realistic. And that's what these deep fakes are. And it's actually pretty insidious, especially because we're nearing an election season here in the US. You can actually have a video that looks realistic of some political figure saying something that's absolutely horrible that would impact the choice of the voters. And so this idea of detecting deep fakes is a pretty serious one, and deep fakes are possible now, right? So that's very interesting. Now imagine you have another one is in some of these models, if you can sample, you can produce things like voice, right? There's an experiment where Google uses a conversational agent that can listen to voice and respond appropriately. And the idea is to use this to deal with telemarketers, right? So you can imagine you have this thing on your cell phone running indirectly through a cloud. If you get a call from a number you don't recognize, you just say, send it to my conversational agent. And this conversational agent will answer the call, interact with the person, and give you a transcript, either audio transcript or written transcript of what that interaction was, so you can find out if it was a legitimate call. So supervised learning, in deep learning, you have these generative models, and for supervised learning, you have convolutional neural networks, and you can also do sequences, things that are temporal, something called recurrent neural networks and extensions of RNNs, right? Now, with unsupervised learning, excuse me, again, with unsupervised learning, you don't have labels. You're looking at aspects of the features that describe your data points. Autoencoders is a way of kind of summarizing the values, almost clustering them together. And then this thing called stacked denoising autoencoder. You have autoencoders that are outputting to autoencoders, outputting to autoencoders. You can think of it as a quantization of your data that is in multiple levels. One output of a model is outputting to another output, outputting to another model, and so forth. And so if you convert, if you excuse me, I'm running out of voice. If you combine supervised with unsupervised learning, you get GANs, generalized adversarial networks. And so from the unsupervised standpoint, you can sample from them, just like how I described. You get some clusters, you fit a distribution to it, you can now sample from this distribution. With the supervised learning, you can classify things, you can take inputs, and you can cast them as one of some number of categories. So if you have some unsupervised model and you can sample from it, you sample from it, and then you classify it with the supervised portion. And so this idea of generative adversarial networks, it'll basically explore artificial examples that it creates through sampling and then score them using the supervised portion. Okay. Any questions about this? Does that make sense? All right. So this is a GAN, and this is just an idea. You have a generator network, and you have some inputs, and so it's generating something by sampling, and the output would be something that looks like poetry. and then you take that poetry into a discriminator, that's your supervised learning, and then you take what looks like real Shakespeare poetry and you compare it against the generated output, you score it and say, yep, this is Shakespeare, or nope, this is not Shakespeare. And if you keep doing that with enough samples from your generator network, you'll eventually find it'll learn what it means to generate a realistic sample. And that's exactly how these fakes work, and is doing it for video, which is pretty interesting. You can do it for audio, right? You can do it for video. You can do it for text. And so you can imagine, in essence, this GAN is almost like an author, right? And that'd be interesting if you feed it different genres of literature, and then you say, what happens if I mix this genre with that genre? Imagine for paintings, what happens if I mix the Impressionist period with the Andy Warhol period? I don't know what it is. I can't remember. But you get some, Van Gogh meets Warhol, whatever that would look like. And so imagine then, you can do this with all sorts of things, right? Um, and so the idea then is you use the supervised portion as the scoring mechanism that helps you prune through which one of these generated things looks realistic. And then eventually you learn how to produce things that are reasonable or appear realistic. Okay? And so this is a pretty big deal, right? You're exploring the space of possibilities informed by distributions over real things and then using it to score new ones. So imagine then if you design a song, right? This way, music. Who gets the Grammy Award? You or the model? That's an interesting conversation beyond the scope of this class. So is it being creative? No. It's just really exploring. So what if you feed it two genres of music? You feed it classical and you feed it country and western. So you get classical, country, and western, right? Whatever that is. If you win an award with that, right? Who gets the award? Who gets the award? I don't know. That's an interesting question. Or was it who provided the data? Who put it into now? How do you do copyrights? Whose copyright is it? Hmm. Is it based on the works that you input for the generative part? Mm-hmm. 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 Or imagine, to kind of piggyback on your thesis, what if you put soccer plays in it and it created a new play and you tried it in a game and it worked well, right? And they find out that you did this. Now all of a sudden, everyone's going to design plays for some sport using this approach, right? So all sorts of possibilities. All right. Anyways, so GANs are pretty exciting, and these things combine supervised and unsupervised learning together. And so, we are still in the early stages. We are in sort of the desktop big IBM PC with 8 kilobytes of RAM phase of the computer revolution, right? With this. So imagine 20 years from now where this stuff is going to go as you have more sensors, more compute power, and so forth. This is very, very exciting where it's going to go. Now, of course, from an ethical standpoint, a model is only so good as the data that you give it. And so there's this community that's growing that talks about fairness in AI and ethical AI algorithms. And so, for example, and you can also imagine if you have a criminal network, right, and you're trying to ascertain whether someone should arise suspicion based on what they're doing, if you have video of people doing suspicious things, depending on how the people appear in the video, it's going to key in on things that are easy features to key in on. So you can imagine things like ethnicity, things like gender, and stuff like that, and all sorts of other insidious places where this thing could go, right? And so it's really important as scientists in this discipline that you understand what can go in on the front end in terms of the data. You want to have data that's representative across a broad swatch of the population. If this data is going to impact more and more of our lives, you want to make sure that it is serving everybody well. Okay. All right. Any questions about this? All right. So there's also reinforcement learning. Now, reinforcement learning always seems to get left out a lot in machine learning, and it's a very powerful mechanism. And reinforcement learning is based on the dopamine response in animal learning, and it's the idea that a system will explore a number of actions to take based on this idea of a reward function, right? And so similar to how you would train a pet, you give it a tasty treat. If it does something it's supposed to do, it associates that pleasant response with the action and therefore continues to reinforce or select those particular actions more so than other actions. And so this deep learning has also been used for reinforcement learning as well. It's called deep reinforcement learning. Okay. So let's take a look at supervised learning. And so I didn't realize that this was going to be piecewise. Let me just put everything on the slide and then talk about it. So when you have traditional pattern recognition, and again, I still don't like this word traditional, I'll call it human in the pipeline, HIP. When you have HIP pattern recognition, they work with handcrafted features. And typically you have these simple trainable classifiers, and we certainly saw with machine learning all the mileage you can get out of the linear perceptron, right? If you have a nonlinear phi function or kernel, and you combine that with a linear decision boundary in this Z space as a result of using this phi function, you can use the linear model training, which is simple PLA update with a pocket to do just about anything, right? We've seen that. But for the most part, in deciding what this phi function is and in crafting your features, that's where the human in the pipeline comes in. So you have these handcrafted features, and you also select what your feature selection is going to be, whether it's synthesized or subset, and what the algorithm used. In k nearest neighbor, you take the elbow of the graph, and you're going to choose k appropriately based on the scree plot. All that stuff, it's still something that you do, right? So you have these handcrafted features and you train your classifier regardless of what it is, and you have some output. It's tedious and costly to develop handcrafted features. Moreover, you spend a lot of time, 65% or more of your time, energy, and effort is not atypical in developing features in this human in the pipeline approach. And so they're highly dependent on one application. If you're dealing with Netflix movie recommendations, it's very different from dealing with Twitter feeds for sentiment analysis. All the features change, and typically, when you're working in one of these domains, you're so specialized that if you become a Twitter text classification person, it's really hard to get a job doing image classification because you spend all this time building up this machinery and this expertise in the domains for the features for a particular type of data source. And so with deep learning, it has an inbuilt automatic multi-stage feature learning process, and it constructs these rich hierarchical representations. So let's say we have a raw image input like the following on the left-hand side of the screen. You learn these low-level features. So these could be like simple edges at various very basic colors. And then you take these low-level features, aggregate them together in so-called mid-level features. These might be lines or it might be corners or it might be very simple shapes. And then you take these and combine them into high-level features. You take aggregates or complexes of your mid-level features to construct things like window frames or textures in fabric and so forth. And then you have even higher level features. You put these mid-level and high-level features together and you get whole objects like sinks and doorways and things like that. And you use that in your trainable classifier and get labels like indoor, outdoor for high-level concepts. And so at each stage along the pipeline, you have an increasingly, excuse me, complex arrangement of these features from the level previously, and you start from simple and work your way up to complex. That's not to say you could take something that looks like a sink and add a box above it if you have a sink that's by the window. It doesn't say you only have to use mid-level features as the basis of high-level features. You could take a high-level feature that adds some low-level features in order to augment something at a high level to look like some object of interest. Okay? All right, any questions about that? All right. So here, for an image, you can imagine you can imagine a simple pixel, which is the most fundamental unit of data in an image, right? Everything arises from a pixel. You have pixels that occur in a certain succession nearby one another to construct an edge. An edge is just a change in pixel value. And you take edges and you put them together, you get a texture, right? and you put textures together, you get something called a motif. And then you put motifs together, you get a part, and you put parts together to get an object, right? Likewise, in text, you might have a character, which is it doesn't have to be also Western character. It could be another type of character, Eastern character, or what have you. You put characters together to form words. You have word groups to give you phrases. Phrases together give you clauses. Clauses give you sentences. You put sentences together to give you a whole story. And so, in essence, with deep learning, you can take your low-level features, most simple fundamental unit, and you'll notice these fundamental units are directly from the raw input. There's no feature processing that happens. And what you're doing is you're growing the feature representation by aggregating these increasingly complex hierarchies of these low-level features to construct your descriptions for your classifier. And this works quite well. You can also see why these things need so much data. Because if you're going to start from the low-level pixel information, right, even just for grayscale, you have 255 values. And if you have an image that's 10 by 10, that's 100 times 250. You have 100. I'm sorry, 255 to the 100 power. And that's how many different 10 by 10 grayscale images you can have. And so if you're going to construct directly from the raw signal information, from the most atomic or smallest unit of raw signal, you need a lot of examples to span the space of all possible exemplars that you can have if you want to find the assembly from simple to complex arrangements that are descriptive of what it is you're trying to do with that data source. Okay? All right. Any questions about this? And so each module transforms its input representation to a higher level one, the same way the human and biological learning does in the cortex, the visual cortex and the audio cortex. Okay. So let's take a look at how this might work. Take the time. Close. Low power mode. Oh, 5:16. 5:45. Okay, we have about 29 minutes. So this is the usual setup for a neural network. You have your input layer, and your input layer represents your raw signal. And in the case of a deep network, it will be a raw signal. Last semester, when we talked about neural networks, we assumed that the input was some feature representation. But here, we're going to extend that, and we're going to think of our input as being the raw signal. And you have a bunch of hidden layers in between, and then you have, of course, your output layer. And so your output layer has a hypothesis, and you have this weighted sum, and here are our weights, W1 for the weights between the input layer and the hidden layer, and then W2 for the weights between the hidden layer and the output layer. And here we have a single hidden layer. Now, of course, in a typical deep learning network, you're going to have more than one hidden layer, and it's called a deep network because you have a very deep network, right? Meaning that you have very many hidden layers. And you can think of a hidden layer as being some weighted sum of the raw input. So we have some weighted sum in the case of your input being an image. Your input image would be individual pixels. And now you're saying in the first hidden layer, you have some weighted sum of pixels, right? And so, of course, if you're going to use this to describe objects in an image, you need a lot of these layers in order to have first order combinations, second order combinations, third order, fourth order, and so forth, to go from pixels to edges to other shapes to objects and then to categories. Okay, and so in this particular case here, my hidden layer H is just some function sigma of weighted combination of the inputs plus a bias term, and then Y is just weighted combination of the outputs of the H layer before it, the output layer on the right, your right, W2H plus a bias term. Now, of course, this sigma is a so-called squashing function, and that squashing function is often it can be linear if it's just identity, or it can be nonlinear, and that's how you add nonlinearities to this. So if you think about it, it's just a layers of composition, and if you get to the output, you think of that as some nonlinear function over the weighted sum of some input, and that input itself is a nonlinear function of a weighted combination of another input. So it's just some composition of a composition of a composition of a weighted sum of a composition of a weighted sum of a composition, and so forth. And so, from a machine learning perspective, it's nothing more than a particular type of function class, hypothesis set, which takes form as the set of functions which are weighted sums of nonlinear functions and the compositions of weighted sums of nonlinear functions. Okay, and that's all it is, right? Um, so this is a very simple example of a neural network. And in this particular case, we have 6 neurons, not counting the inputs. We have 4 neurons in the hidden layer, 2 neurons in the output. And if you look at the weights that we have 3 times 4. So we have 3 in the input, 4 in the hidden. So it's each one contributes 4 edges, each one of these 3 input nodes. And so each weight corresponds to a parameter, right? And the bias term is also a parameter. So we have a total of 3 times 4 plus 4 times 2, which is 20 total weights. And then the bias terms, each node has a bias term because it's W transpose X plus B, right? We have 4 biases because we have 4 hidden nodes in the hidden layer. And then we have 2 biases because we have 2 2 nodes in the output, right? And so we have a total of 6 biases and 20 weights for 26 total learnable parameters. And so another reason why these networks need a lot of data, right? They work well with a lot of data. This is just a very simple 3 input, 2 output neural network with 1 hidden layer, but you have 26 parameters. And of course, Hoeffding's inequality and computational learning theory does not change just because you have a cute way of constructing a function and searching through hypothesis space. So of course, with 26 learnable parameters, remember there's an exponential relationship between the amount of data you need and the dimensionality. And the dimensionality corresponds directly to the number of parameters that you have. So if you have 26 parameters, that's a pretty big amount of data that you have for just a simple network. And this gets even worse. This is just a single hidden layer. Imagine if you had 10 hidden layers in between the input layer and the output layer. That's why you need these millions upon millions of data points. Okay? And so, again, still, the jury's still out about what architectures of this network graph allow you to learn certain types of things. In addition, you don't get around this idea of VC dimension, right? That's the law, like gravity, it's the law, right? It just is. And so, what would be interesting is to see how performance changes and what architectures you need. Do you need slim and deep? You need wide and short? What do you need as you decrease the amount of data that you have? How do you learn? Okay, and what can you learn? So this idea of computational learning theory for a deep network, the jury's still out because we don't yet know what particular architectures are good for learning what types of things. We still don't know that. Yes, you input the raw data and you have a big enough network that can handle complexity and you give it enough data, then it'll produce beautiful results. Absolutely. So it's still in early stages, but nonetheless, it's being used in some fantastic applications, and deep fakes is just a really, really wonderful, interesting example of that. Okay. Any questions about this? Okay. Hmm. Hmm. Yes. Oh. Oh, wow. Yes. Hmm. Hmm. Yes. Hmm. Yes. Interesting. And social media being what it is, it doesn't take a lot for something like that to propagate wildly. And sadly, even with printed text, a lot of people don't read the article. You could have a headline that said, so and so in the Conservative Party endorses someone in the Liberal Party or the Labor Party or whatever. And then in the article, it'll say, this is a fake, right? And about 50% of people, oh my gosh, and then they're going to forward it and no one reads it. And so imagine now with the video, it's even worse. No one really scrutinizes. Hmm. Hmm. And so, from an ethics standpoint, and, Facebook didn't create the problem, but they helped the problem propagate. And so one of the questions you have to ask from an ethics standpoint, now, will there be a watermarking, like there's a certificate, and if it's not digitally signed by the actual entity depicted in the video, you don't know it's authentic. And you'll notice in U.S. elections, it'll say, um, I'm, uh, I don't know, we think of it. I'm Joe Biden and I approve this message, right? You'll notice that they say that. And the reason why they say that is because if Joe Biden didn't approve that message, he's not speaking on that. Someone's saying that on his behalf, especially because companies are considered people in the United States. Companies can put out ads on behalf of a political candidate and get around the limits for donating to political campaigns. Um, so that being said, perhaps at some point in the future, because of deep fakes, you'll have digital watermarking on videos. So at least that way, from a digital certificate standpoint, maybe everybody gets a birth certificate and a digital certificate, and then if it's not signed and authenticated as being signed by that person, then it's known to be a fake. You can't trust it. Now, a company like Facebook, Twitter, Instagram, all those, they could do that 6 months' time, no problem. Month or two's time. It's not a technology issue. Do they want to do it? Probably not. Will it get bad enough that they might? Who knows? We don't know. They'll be forced to, unless because they profit off of somebody buying ad space and saying disseminate it to people who fit this profile. Hmm. 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 Yes. Yes. Hmm. Hmm. Absolutely. Hmm. And it doesn't even have to be something as direct as that. It could be something as innocuous as, okay, I have a demographic, and let's just say the demographic is people who have less formal education, whether it's primary or secondary, post secondary, or what have you. All I need to do is convince you that election day isn't Tuesday, it's actually Thursday. So then you believe that, not wanting to check on that, and then you wait until Thursday. I'm sorry, election was Tuesday. It's too late. You can't go vote after the fact. And if you can convince enough people in a certain demographic that that's the case, you can actually skew an election, in particular for the local elections. Because even here in Dover, the winner of the mayor election is only by like less than 100 votes, right? And if you think about the House of Representatives, one representative for every, I think it's 600 or 700,000 people, right? Yes, it's every 700,000 because Delaware only has one. We only have 900. Yeah, it's one for every 700,000 people. So you only need to sucker, well, 10,000 people, you do it enough and they believe it, you don't have to do that much work to convince people that voting is a different date. And when they finally realize it's too late, right? So yeah, it's really insidious, and there has to be some mechanism. I think watermarking and certificates, that's doable now, and it's just do they have the will to do it? Because it's profitable, right? Um, a candidate, Elizabeth Warren, she tested out Facebook by by that was brilliant. I thought she bought a campaign ad that was obviously fake, talking about, I don't know if it was the current president or who she was talking about. No, it was the current president, and she said that he is going to sign the Paris Accord treaty. He's going to do all this environmental stuff, like just stuff that was just anybody with any bit of sense would know that it's not true. But she did it just because she wanted to see if Facebook would tag the ad and say, no, this is not true. And they didn't. They gladly took the money and posted the ad, and it got disseminated, which was actually brilliant. Somebody do that. Uh, so, anyways, so that's about the ethics part, and it's going to become a very serious thing as this pervades its way into society. So imagine you have a surveillance video. These these Ring doorbells, right? These doorbell security things. With a deep fake, you could make it look like your neighbor just broke into your house. Mm. And then you notify the authorities, or you report something stolen, get the insurance claim, right? This is going to be a real problem. So there's lots and lots of insidious things that can happen. And so this idea about authenticity and authorization and certification is going to be a real problem, a real issue there is going to have to be addressed at design time, not just after the fact. Okay, so we have our weights, we have our activation functions, and then the question is, how do you train? So if we see this really cool animation, I'm going to do that again. Um, we walk the gradient, and we label each data. We have a forward iteration through the data, and we run back propagation. And as we do so, we're adjusting the weights, and we're searching for those weights that give you good performance. I always love animations like that, or loops. Okay. And so this cost function is the objective, and it's taking a measurement of the difference between the ground truth as it pertains to the target function and the output of your network. And it's basically computing the gradient with respect to each of these weights in a layer-wise fashion going backwards through the network. And I won't cover that since we did that in machine learning already. It's the same back propagation. And so essentially what happens is that you update each weight some proportion relative to its responsibility, if you will, towards the error that is seen ultimately at the output, right? And that adjustment happens layer by layer by layer on the backwards pass using the local gradient. Okay. And it's really just an application of the chain rule. And so this is an example of what a forward pass might look like. It uses term frequency, inverse document frequency, which is a measure in NLP of effectively the importance of a word to a document. And so here we have W, our weights, XI is our TF IDF vector. And so each one of these positions would represent a TF IDF score for each of those word stems. And then we have our bias term here, and then we have the output of our nonlinearity sigma on the result of W transpose X plus B. Okay. All right. And so, of course, based on what these outputs are, you might score something relative to its appropriateness for whatever task of interest that you have. All right. So let's take a look at these activation functions. We talked about this W transpose X plus B. We have about 10 or 12, 13 more minutes. These activation functions are responsible for adding this nonlinearity to each one of your nodes. Now, of course, in order to learn complex decision boundaries, you need nonlinearities, right? Second order nonlinearity, like a quadratic, will give you a basic parabola shape, and you can kind of squash it in, or you can have it more flattened, depending on the coefficient. Certainly, as you increase the order of some parameter, like a power, if you will, a polynomial, the degree, you're going to increase the complexity of that boundary. And so, or the degree of nonlinearity. And so, therefore, you need activation functions. Since you have weighted sums, W transpose X plus B, at each layer, you need a nonlinearity to get these complex decision boundaries in order to shatter your data in feature space. And so as you add more hidden neurons, you go from 3 hidden neurons to 6 to 20, you'll notice you get more nonlinearity, right? The ability to kind of carve out shapes, if you will, in feature space in trying to separate data points of one class from data points of another class. And so there are different activation functions. Sometimes it's called a squashing function, and I'm certainly not going to go over all of them. I'm just going to touch upon a small handful in the next 5 or 8 minutes. So sigmoid activation function, it takes your signal, W transpose X plus B, and it puts it through this sigmoid 1 over 1 plus e to the minus x, where x is going to be that signal, that score, W transpose X plus B. And it maps it from a real number, whatever that weighted sum is, to the interval between 0 and 1, right? And some people think of the sigmoid as kind of a type of probability, right? And this is nonlinear, and you can think of it as the firing of a neuron. But sigmoid will saturate, meaning that if your signal coming in is large enough, it'll peg it to 1 or something close to 1, and it won't go any further down. And so sigmoid is one type of activation. The other is called the tanh, right? The hyperbolic tangent. And there's the functional form, 1 over, I'm sorry, rather 2 over 1 plus e to the minus 2x minus 1. And the tanh function is similar to sigmoid, but when it maps your signal to another range, it maps it to the range between -1 and +1, right? You can almost think of this as, you want to say the minus class or the plus class, if you will. But this one, excuse me, also saturates, but the output is centered at 0. So when we talked about in classification sign W transpose X, you're looking to see if something's greater than 0 or less than 0. The tanh kind of fits into that naturally in terms of the range to which it maps your score, W transpose X plus B, but it does it centered at 0. Okay. And so then we also have something called ReLU, which is the rectified linear unit. And it kind of looks like sigmoid, but it has some efficiencies, if you will. If the signal is negative, ReLU returns back a 0. And if the signal is positive, that W transpose X, it gives you exactly that signal itself. And so rectification is a term from electrical engineering that says to make something positive, right? Or to make it so it won't go negative. And when you go from alternating current to direct current, you usually have something called a silicon rectifier. And it says every time your voltage goes to negative, it keeps it at 0, right? And then you use a capacitor to smooth the humps and make it a continuous current. But nonetheless, what this ReLU does, it's a type of activation function, and it takes a real valued number, the result of W transpose X plus B, and it returns back one of two things, either the value, X, if it's greater than 0, or 0. So it takes the max between 0 and your signal input to that ReLU nonlinearity or squashing function. So it maps from real number to the positive real numbers. Okay, all right. And so this ReLU, it trains much faster, right? Because you don't have this complex derivative when you're trying to do the back propagation. And because it trains much faster, it accelerates the convergence of any sort of gradient method, including the stochastic gradient descent. Now, stochastic gradient descent is just like gradient descent, only you're randomizing the selection of which axis, if you will, along which you compute this gradient. And so it's linear and it does not saturate. And that's the reason why this is much faster. And so by using these ReLUs, you get sigmoid-like behavior going from 0 to something that's non-zero, but it's much faster. And this can be one of the speed-ups, if you will, to help a deep learning network train much faster. It's expressive, and it also prevents what's called the vanishing gradient problem. This vanishing gradient problem refers to the fact that when you do a stochastic gradient, you'll notice here for the tanh and also the sigmoid, it's more so going to be a fractional quantity that outputs from each node between 0 and 1. And so if you're doing the gradient with respect to something that is between 0 and 1, it's going to have a multiplicative effect because when you look at the gradient, it's the chain rule, right? And so chain rule, you're multiplying some partial derivative times some partial derivative, sometimes partial derivative. And if you have a long or deep network of these partial derivatives that you're multiplying with one another for chain rule, at some point you multiply a fractional component, a decimal, with another decimal in enough terms, it's going to get really, really small, and your weight's going to go to 0. And it's called weight decay, right? And that's called the vanishing gradient because it's going to go to 0 because once you get so deep in the network, you have enough terms in your chain rule that are between 0 and 1 that it's going to go to a really small value, effectively 0. And so this ReLU solves the vanishing gradient problem because you can see here, it just keeps going up, right? And you have larger values to key into when you compute the iteration backward pass for this gradient as you go from output layer down to the input layer. Okay, so it's less expensive, the gradient is easier, and it accelerates your training, and you still have overfitting, right? You want to make sure, of course, that you have enough data, but you also want to make sure that you encourage your model to make reasonable choices and not fit the noise in the data. And so, of course, because you have so many parameters, we saw 26 parameters for just a 3 input, 4 hidden layer, 2 output layer network, right? Just 26 parameters. So there's an opportunity to overfit your data with those 26 parameters, or even just a small network. And so, like anything, any model, you want to overfit. And how we overfit is using something called dropout. How you prevent overfitting, i.e. regularize, is by using something called dropout. And what a dropout node does, it's a type of node in a deep network, is it has this dropout probability. And what it does, it says, okay, I'm going to, with some specified probability P, I'm going to shut off certain edges, right? Randomly or not randomly, with some probability P, I'm going to select some of my edges that are inbound, and I'm going to set them to 0, right? And so what does that do? What that does is that it forces your model to learn weights different from what it otherwise would have. So let's say you're doing stochastic gradient descent or just regular gradient descent. And let's say on your backprop iteration on this top node, let's say it preferred to update this weight the most in its iteration on the backprop. With that were a dropout node, what it would do is that probabilistically on one iteration, so because it's probabilistically, from one iteration of backprop to the next on the backwards pass, maybe that node's weight might be shut off, and sometimes it's not shut off. And for those cases when it's not shut off, it does regular update to the weight for that parameter. When it is shut off, it forces that network to select other weights, other parameters. So it's a way of adding a little bit of noise, if you will, to the system. And it's akin to doing mutation in a genetic algorithm. You're forcing it to explore other solutions. And if you have forcing it to explore other solutions, you're not sort of getting on this pathological edge condition where it always visits one section of hypothesis space. Because if you think of what's happening, you have this deep network, but that deep network still, in terms of the function definition, it still corresponds to, and I'll do it in, there it is, it still corresponds to a big set of functions. So without regularization, what do? You might be exploring compositional functions that correspond to this small region of hypothesis space. So the moment you do this dropout, now you're depriving it from the ability to explore that region, and now it's forced to explore another region, right? And so by doing this dropout, and from one iteration to the next, those weights that are dropped out can change, right? Because you're going to drop out weights. Maybe it's probability 0.05, so 5%. When you make the decision of whether or not to drop out a weight, that probability is going to be 5%, right? So now it's exploring this region. Now it's exploring that region. Now it's exploring that region. And so you get more robust models because you're not pre-committing to a pathological region of hypothesis space. And that's how you regularize a deep learning model with a dropout. Now, of course, if you set your probability P too high, all right, your regularization parameter is considering the regularizer more so than the loss function, which is to bring closer together the performance of this model with the ground truth target function. Okay, all right. And then you can also do weight decay and early stopping. Weight decay says if a weight gets too small, just drop it to 0 because it doesn't matter anymore. Dropout is different from weight decay. Dropout takes a weight that otherwise would have been updated with your backwards pass on your back prop, and it excludes it from consideration by, for that pass, it's setting it to 0. It's dropping out of your computation, out of your model. Okay? Does that make sense? Okay. Okay, and of course, loss functions. There are different types of loss functions we can have. For classification, the output can be one-hot encoding, where you have the difference between the agreement of your class label outputs on the end of the network. On the output layer, you can have softmax, where you convert your representation for your output to a probability distribution, and you're looking at the label that is associated with the largest probability. And you can also have cost function that uses cross entropy, which is the difference of agreement between the predicted labels and the ground truth labels. For regression, you can use sigmoid linear identity function, mean squared error, or the mean absolute error is a take on mean squared error that uses absolute value. So that's all I had for today. With that, we will end there. Please be aware of key dates. Please look out on the blackboard for the final project. As usual, please stay healthy, stay safe, and I'll see you all on Thursday.